Welcome back. So hopefully we now have a better picture of some of the model architectures that we need in different applications. So for this lecture and the next few lectures, we're going to talk about some training techniques and heuristics that we use to make sure that we can effectively and efficiently and successfully train these architectures. So in this lecture, we're going to talk about two techniques that we call initialization and normalization. So initialization. So basically, how should we initialize the weights of these architectures? Okay, and whether initialization matters or not. So obviously initialization matters, and the reason for that is that these deep learning architectures are complex, okay, and they dictate the kind of the loss functions that we're gonna deal with. So because these are convex, these are highly complex, the loss functions are going to be highly complex as well, and they're going to be basically highly non-convex. Okay, so lots of ups and downs, as we can see in a figure like this. So given this, it really matters where you start your optimization. Okay, so again, if I, let's say, start here, okay, I'm going to find a suboptimal solution. Whereas if I start here, I may actually find a better solution. So in this case, the better solution means a better fit to the data, and hopefully, therefore, a more generalizing model. Okay. So therefore, initialization is important to make sure that the solutions we are finding by our iterative optimization and training algorithm is of high quality. Okay, and one of the things we're going to talk about is that initialization, especially early on, is also very crucial in terms of the gradient information. Okay, so gradient information is a learning signal. So if that information is useful, we should be able to, let's say, be more effective in optimizing our model. But if that information is not useful, the training process is going to be slow or even unstable. Okay. So the idea is, therefore, we want to find initialization techniques that help us to have like a better training process. Okay. So let's consider a multi-layer perceptron, and we're going to consider this to point out two potential issues that could arise, and therefore see how we can leverage initialization techniques to mitigate them. Okay. So what was a multi-layer perceptron? So it's basically represented by this mathematical equation here. Okay, so the output of each layer, or the activations, are basically the activations of the previous layer times some weight metrics plus some bias, and then we apply a nonlinearity, basically an activation function, such as, again, ReLU or sigmoid. Okay, and let's say we have L layers. Okay, the first input is X, the last output is basically our prediction. Okay. And as I mentioned, B's are the biases, and W's are the learnable, the weights, which are the learnable parameters of the, let's say, the JS layer here. Okay. Okay. So we mentioned that our learning signal is basically the gradient, right? So that's the quantity we're going to use in the SGD and other advanced training algorithms we're going to talk about to update the parameters of the model. Okay. So let's see what's the shape of this gradient. Okay. So essentially, if we want to update B's, we need the partial derivative of the loss with respect to each Bj's. And if I want to update Wj's, I need the partial derivative of the loss with respect to Wj. Okay. So here, what I'm trying to do is to basically see what's the shape or the form of the partial derivative of the loss with respect to Wj. Okay. the weights of a JS layer. Okay. Now this could be a little bit complicated because W's are matrices, so the loss of a scalar value function with respect to a matrix, the gradient of a scalar value function with respect to a matrix is basically a matrix. Okay. So to make things a little bit simpler, at least for myself, what I'm doing here is that I'm thinking of each Wj as a vector. So I'm vectorizing this matrix. Let's say I'm stacking all the columns into a very large column vector, okay? Where the size of that column vector is basically dj times dj minus 1, okay? All right. Okay, so our goal is to find this partial derivative. We can use chain rule, okay? So therefore, the partial derivative loss with respect to Wj is basically the partial derivative of the last activation with respect to Wj times the derivative of the loss with respect to the last activation, okay? Now I can again apply chain rule to this component here to basically decompose this derivative in terms of the product of a bunch of derivatives, okay? Right. So one thing to note here is that h is basically a vector, and we are taking the derivative of a vector with respect to another vector. So the outcome will be a matrix, okay? So therefore, we can use chain rule to represent this matrix as the product of a bunch of other matrices, as I'm showing here. Again, by chain rule, this partial derivative is equal to the derivative of the output of the JS layer with respect to Wj, the derivative of the output of the j plus first layer with respect to hj, and so on and so forth, until the derivative of the last output of the last layer, or the last activation with respect to the activation of the layer L minus 1. And finally, I have this derivative of the loss with respect to HL. And this guy is a vector, because I'm taking the derivative of a scalar with respect to a vector. Okay. All right. So therefore, this is the shape of the gradient. Okay. So we have some matrix here, some vector, and then the product of a bunch of other matrices. Okay. And note that this product is going to get larger as I'm considering the partial derivative of the layers early on in the network. Okay, so this product is going to be the product of more terms for when I'm considering the partial derivative of the first layer compared to the partial derivative with respect to weights of the, let's say, the last layer. Okay. Now, so this is because this is like a product of a bunch of matrices. It could be a very large quantity, or it could be a very small quantity, and that depends on basically the eigenvalues of these matrices. Okay. So our outcome therefore is that our learning signal is proportional to this product, and as I mentioned, it could be a very large matrix or very small matrix, right? So, and that depends typically on the eigenvalues of these matrices. So therefore, two potential issues could arise, right? So if this product is large, we may have the exploding gradient problem, and if this product is small, we may have the vanishing gradient problem. Okay, so what's the vanishing gradient problem? Again, very small product. Therefore, the gradient is going to be small, and what's the implication? Well, we use the gradient to update our parameters. So if the gradient is small, we're not going to update the parameter much, or even at all. Okay, so we're not going to move very far from the initialization. And this has been observed to happen with very deep networks and also RNNs. And the fixes in the literature include basically the LSTM architecture that we briefly talked about, as well as including or adding skip connections to our network, such as residual networks. Okay. So the other problem is exploding gradient. Okay, so it happens when this product is very large, which means that the gradient is very large. So we're gonna overshoot. Okay, so and this could lead to instability. Okay, again, this happens with deep networks, but I would say the fix here is somewhat simpler, and it's something that we have talked before, right? It's called gradient clipping, right? So you just make sure that you have like an explicit safeguarding mechanism that ensures that the gradient is not becoming very large. Okay. All right. So in addition to basically these metrics, these considerations, I should point out the activation choice also matters, right? So because these derivatives are basically hiding the derivative of the activation function in the maths file. Okay. So for instance, what we have observed is that sigmoids are more prone to vanishing gradient problem. Okay, and the reason is somewhat intuitive if you plot the sigmoid function and its gradient. So here's the sigmoid function, and here's basically the gradient of the sigmoid function. As we can see here, the gradient for somewhat moderately large or moderately small numbers is super low. Okay, so it's basically 0. So therefore, if I'm, let's say, initializing the model here, or somewhere in the training, my weights or some of my weights enter these regions, the gradient is going to be potentially very small. So I'm going to suffer from the vanishing gradient problem. Okay. All right. So in addition to these two problems, there is, I would say, another problem that motivates the use of randomness when initializing neural networks. And that's the problem with symmetry and potentially limiting the capacity, the learning capacity of our models. Okay. So recall, we had this motivation behind introducing nonlinearity and also deep models to make sure that we are increasing the learning capability. So therefore, the performance of a deeper model hopefully is better than a shallower one. And we specifically talked about the role of nonlinearity to ensuring that we have a higher capacity. So that if you have a linear activation, our network basically collapses into a linear model. Okay, so but a similar behavior could happen when we have bad initialization, meaning that we're not going to enjoy a high learning capacity. Okay. So let me try to demonstrate with a simple example. Imagine that I have again like a multi-layer perceptron. So here I'm just focusing on one layer, so layer 1. So so this is basically the output of layer 1, the activations. So I assume that I have 2 neurons only. Okay, I have some nonlinear activation, let's say ReLU, and then this is basically the product of weight matrix and the bias. Okay. All right. So let's make the following assumption. So we assume that our initialization is such that all of these weights are the same. Let's say there are some parameter alpha, and all of the biases are also the same. Let's say beta. Okay. Now it is not difficult to show that H1 and H2 are the same. Okay. So at initialization, the output of my model is the same, or the output of my neurons are the same. So I have 2 neurons, but they are acting exactly the same. Now, it is also not difficult to show that the gradient, the partial derivatives, are also the same. Okay. So what's the conclusion? The conclusion is that if I'm using gradient-based updates to update the parameters of my model, let's say Wij's and Vj's, if I start at the same place, I'm updating these neurons to be the same. So throughout the training, these 2 neurons will remain identical. So despite having 2 neurons and therefore hopefully a high learning capability, I'm actually going to have just basically 1 neuron. So therefore a lower learning capacity. Okay. So there is a symmetry here, therefore. So our two neurons are reducing only to one neuron. Okay, so and the capacity is reduced. And this is an example that is easily avoidable if we were to introduce randomization. Okay, and we're going to use randomization a lot in optimization of deep learning models. One place we use it is basically in the stochastic gradient descent algorithm itself. So our updates are basically randomized. Another place we use it is actually an initialization. So we're going to use randomized initialization to avoid this symmetry issue and also mitigate the vanishing and exploding gradient problem. So one very famous initialization technique is basically the Javier initialization. It's named after the name of the person proposing this idea. So the main idea is that we want to initialize the weights such that we don't change the signal strengths much. Okay, so as a result of, let's say, these matrix products, these vector products, we're not going to change the strengths of the input signal much. Okay, and so we want to make sure that this happens when we process the information in the forward direction and also in the backward direction. Okay, and the main idea for that is that the way we calculate these gradients, as we're going to talk about in our future lectures, is through the backpropagation algorithm, which requires us to traverse the network in both forward and backward directions. Okay, so therefore, what we want is to make sure there is no drastic reduction or amplification in the signal strengths, which could lead to vanishing and exploding gradients. Okay. Now, for our derivation, we're going to, let's say, consider that the activation is linear, or you can say that I'm going to assume that I'm acting, let's say, in the linear regime of our activation. Okay, so for instance, if my let's say at initialization I'm in the areas like in this region, it is safe to say that almost all of my activations are linear. Okay, so for the sigmoid, I can replace it, let's say, with the linear line. Same for the ReLU activation, and same for the Tannish activation. Okay, so for the next derivations in the next slides, we're gonna basically make this assumption. All right. So now let's consider a specific layer. Okay, and I'm setting the bias to be 0 without loss of generality. So let's say that I have a layer where the dimension of the input is the in, dimension of the output is the out. Okay, and let us call the input and output x and o for simplicity. Now we need two conditions. So we said that if we traverse a specific layer from in the forward and backward directions, we are not changing the strength of the signal much. Okay, or in fact, we want to make sure that we don't change the strength of the signal at all. Okay, so therefore we're going to have two conditions. Our forward information propagation condition is as follows. I want the strength of the output, which we can denote it with let's say the second moment, basically, the expected value of the norm of the output square, to be exactly the same as the strength of the input signal. Okay, so here the strength of the output is basically this expectation. So we can expand it out. So this is going to be basically the sum of each of these OIs a square. The strength of each of these OIs is a square. Okay. And what is my output? I'm again assuming that I'm in the linear regime of my activation functions and there is no bias. So each of the output is basically this simple product. Okay. All right. So this is when I'm feeding x to this specific layer, meaning that I find the product of x and w, and then I get the output signal. Now, in the other direction, in the backward direction, I want to still make sure that I'm not disturbing the power of the signal by much. Okay, so in this case, let's say I'm feeding O in the backward direction to my network, and my output is basically x. Okay, so in this case, the power of x is basically going to follow a similar expression, and it's going to be basically the product of w and O. In this case, I'm feeding O in the backward direction to this specific layer. Okay. Now let's make some simplifying assumption. Let's assume that the strength of each coordinate of the input x is some gamma in square, and for O, let's say it's gamma out square. And also, let's say that we are utilizing random weights. Okay. So we're going to make sure that each of these coordinates of the weight matrix are independent, zero mean, random variables with variance sigma square. So our goal basically would be to find a very nice sigma square, a very nice variance or noise strength to make sure that these two forward information propagation and backward information propagation conditions are satisfied, such that we are not again amplifying or reducing the strength of the signal much. Okay, so our conditions therefore imply that after some simplification, imply that basically from the forward information propagation condition, d out, because I have d out number of outputs times gamma out, because this is the strength of each of the outputs, is equal to d out d in sigma square gamma in square. And you can see that d out appears on both sides, so I can get rid of it. And similarly, in the backward information propagation condition, d in gamma in square is d in d out sigma square gamma out. And again, d in appears in both sides, so I can get rid of it. Okay. All right. So this is basically the condition that we want, right? So when we process the information in the forward or backward direction, we don't want to the strength of the signal to change at all. So that means that I want gamma in square to be exactly gamma out square. Okay. So these are the conditions we drive in the previous slide. Okay. If gamma in and gamma out are the same, therefore I'm gonna arrive at this condition. So 1 is equal to d in times sigma square, and also 1 is equal to d out times sigma square. Okay. So basically, we want sigma square to be inversely proportional or the reciprocal of 1 over d in, and also we want sigma square to be the reciprocal of 1 over d out. Okay. So in many cases, d out and d in are not the same. Okay. We are changing, let's say, the size of the image as we process it in the network. Okay. So we basically settle for the following. So we set sigma square to be the reciprocal of the average of d out and d in. Okay. So therefore, we basically find like a nice formula for the strength of these randomly initialized weights. Okay. So we set each weight to be a zero mean random variable, which is independent of the other weights, such that its variance is given by this formula. Okay. Now we have to make a decision on which distribution we want to use to sample these random weights. And typically, we either use the Gaussian distribution, okay, so zero mean with this specific variance, or we use the like a uniform distribution, which is symmetric around 0, again with the variance which is proportional to sigma square. Okay. All right. So this is basically the Javier initialization. In terms of some modification to this. So here I mentioned we use the reciprocal of the average. Average can be the arithmetic average, Okay, so basically d in plus d out over 2, or the geometric average. So both of these are valid options in practice. Another modification is that in many situations, we are basically using the ReLU activation. Okay? And one implication of that is that when we are processing a signal, it is likely that we are dropping half of the signal. Okay? So therefore, we will compensate for this by increasing the variance with a factor of 2. Okay? So essentially, the idea is that, let's say I have a symmetric input x. So think of it like a random variable. Let's say a normal random variable which is symmetric around 0, or let's say uniform random variable or a binary random variable. Okay? If the variance of this random variable is, let's say, again, gamma in a square, as a result of feeding it to ReLU, the strength is not going to drop. So the variance, and this is a very simple calculation to show that the variance is just going to be gamma in a square divided by 2. That's why we increase the noise power by a factor of 2 to make sure that we again have this condition satisfied. So this is the one of the frequently used initialization techniques, random initialization techniques. In the next video, I'm going to talk about another kind of ideas that we use in practice to deal with the issues we mentioned. I'll see you next time.